Write using sigma notation. 27 minus 9 plus 3 minus 1 plus a third minus 1/9. So in order to do sigma notation, we'll write sigma. We need our index. We'll start with k. It's easiest just to start with 1. That is what we've done the entire time when we're writing the sequence formulas. Now, since we're starting at 1, how many terms do we have? We have 6, so we'll go to 1 to 6. Now we need to find an expression for the numbers 27, -9, 3, -1. We can see that 27 divided by 3 or divided by -3 is -9, or another way to say that is multiply by -1/3. -9 times -1/3 is 3. This one times -1/3 gives us the next term, and so on. So we can see that this is a geometric sequence. We will have 27, our first term, and we're going to be multiplying by -1/3, and we're not multiplying the first term. We'll start on that second term, so we'll need to say k minus 1. Now when we plug in the 2, we'll get a power of 1. We'll always have 1 less multiplying by -1/3 than whatever the term number is. And that's it for this one. Note, you could have started with k equals 0. It is possible, although I don't recommend it especially when we go to part C. We could have started at k equals 0, but this time we would need to stop at 5, and that would give us our 6 terms. It would look very similar to it. We'd have -1/3, but now we would say to the k. So when we plug in 0, that would give us 1, and we're going to get our first term, and then we'll start multiplying by -1/3. For the next one, it's almost identical. So we'll have 1 to 6. The only difference now is we'll have -27 to start with. Note there are other ways you could write this one as well. We could take out the negative altogether and put a power on that, but it's just simplest to stay consistent with what we've done. When we take a look at part C, if you compare it to part A, is very similar. The only difference is part A is a finite sequence or a series, and part C is an infinite. So we're going to go all the way to infinity on this. And as far as the sequence formula, it will be the exact same. Now we're finding an infinite sum. It's an infinite geometric sum, and we know how to find the formula for that. We have 27 times 1 over 1 minus r, and r is -1/3. So 27 times 1 over 4/3. We'll flip and multiply. That'll be 3/4, and that gives us 81/4. A little review of what we did last class, as well as just a review of a few days ago. What I really want to focus on is this next problem. So we have write using sigma notation, then evaluate the series, i.e. find the sum. That's what evaluate the series means. You should know those words. This is multiplying, so it's 1 times 3 plus 3 times 5 plus 5 times 9, all the way up to 99 times 101. Well, we know it's going to be sigma notation. We're told to do this, so we're going to go from k equals 1. We're going to need to compute that upper value there where we stop, and we also need to write an expression for each one of these things. So let's take a look at the first part. The first number in each one of these multiplications is 1, 3, 5, 7, etc. What is this? This is an arithmetic sequence. We have our common difference of 2, so we know that's going to be 2n. And what would be the 0th term? That would be -1. Or we could say 2. What do we have to do to 2 to get 1? And that's going to be subtracting 1. We could look at the second term, 3, 5, 7, 9, blah, blah, blah. And that also has a common difference of 2. And what do we have to do to 2 to get 3? Add 1. And since our index is k, we're going to say 2k minus 1 times 2k plus 1. Now we need to find that upper value that we're going to stop at, and we can say 2n minus 1 equals 99, or we can write 2n plus 1 equals 101. For right now, you can write down both of them, but in general, it doesn't matter. You write down one of them because it'll give us the exact same value. And we get 50. Now, we're going to build on what we did last class, and that would be we're going to multiply this out. So we'll have the sum from k equals 1 to 50 of 4k squared minus 1, and we'll have that in parentheses. We will separate these into two different terms. K equals 1 to 50 of 4k squared minus the sum from k equals 1 to 50 of 1. We did, actually let me finish this first part. We'll factor out the 4. And then, so now we have this. We did this one last class. Remember that when k equals 1, we have 1. When k equals 2, we have 1. When k equals 3, it's 1. All the way up to k equals 50. How many of those are we adding up? We're adding 1 50 times, so that would be 50. Now, how do we deal with k equals 1 to 50 of k squared? We haven't dealt with that, and I'm just going to give you the formula for this, and if you need it on the test or quiz, I'll just give it to you. The sum from k equals 1 to n of k squared, that'd be 1 plus 4 plus 9 plus 16 plus 25, is very similar to our sum of the counting numbers, 1 plus 2 plus 3. It is n times n plus 1 times 2n plus 1, all divided by 6. I'll give you another one. If we sum up the cubes, that's n times n plus 1 over 2 quantity squared. Again, I'll give you these. You just have to know how to use them and when to use them. So now when we apply that here, we have this 4. We'll leave the 4 alone. In this problem, we're looking at this formula. N is going to be 50. So we will have 50 times 50 plus 1, which is 51, times 2 times 50 plus 1. So that is 101, all divided by 6. Take out your calculators, do the calculation. You should get 171,650. Now let's take a look at another example. We'll look at 1, 3, 6, 10. Those numbers should look very familiar to you. We've dealt with those quite a bit now. Again, we're going to write in sigma notation. You said summation notation using sigma. We have k equals 1. We don't know what the stop value is. We need to find the formula for 1, 3, 6, 10. You can look back in your notes and find where we've derived this a couple of different ways. This formula is n times n plus 1 over 2. This is what little Carl Friedrich Gauss did when he was a child. So we come over here and we'll say k plus 1 over 2, and now we need to figure out that top number. Well, we have the formula for the sequence of numbers, and we want to figure out what n is for the last number. So we'll set n times n plus 1 over 2 equal to 6216. Multiply both sides by 2 and square, or multiply it out on the top. So we get 12, 4, 3, 2. Take it and move it to one side. Now this equation can look very challenging, but it's not. We have to find what two numbers multiply to give us negative 12,432, but add to give us 1. How do you think we can do this? We need to find those two numbers that are only one apart that give us this. How can we figure this out in one calculation? Take out your calculator and do the square root of 12,432. That is approximately 11.5. Not 11, 111.5. So what two numbers that are only one apart and are very close to 111.5? That will multiply to give us this. They will be 111 and 112. The bigger number will be positive, and the smaller one will be negative. So we'll say n plus 112 times n minus 111. Check that out on your calculator. If you take 112 times negative 111, we'll get negative 12,432. So we're setting this equal to 0. We get n equals negative 112 as well as 111. Now we don't want no negatives for what we're dealing with here. So we can come back to our problem and we have 111 is our stop value. Now let's factor out this 2, which is actually a 1/2 since it's on the bottom. So we'll have 1/2 times the sum from k equals 1 to 111, and I'll just multiply that out, k squared plus k. Let's break that up. So we'll have 1/2 k equals 1 to 111 of k squared plus 1/2 the sum from k equals 1 to 111 of k. Now this is the formula I gave to you in problem number 2. So we'll just write down the 1/2. Our n value here is 111. So we'll have 111 times n plus 1. So 111 plus 1 would be 112 times 2n plus 1. 2 times 111 would be 222 plus 1, 223. And all of that divided by 6. Plus 1/2. When we're looking at k equals 1 to 111 of k, that would be 1 plus 2 plus 3 plus 4 all the way to 111. Again, that's what little Carl did. And that is the n times n plus 1 over 2. So in this case, it's 111 times 112 divided by 2. And when you multiply all that out, you get 234,136. Let me see if I can do this last problem. Prove that this equals this. That can seem pretty daunting at first, but it's not too bad. Let's take a look at, we'll pick one side. We'll start with this left side. And what does this mean? This means c times a1 plus c times a2 plus c times a3 plus dot dot dot. What's our last one? It's when we're stopping at n, so it'll be c times a sub n. What do you notice about every single one of these terms? They all have c in common. So what can we do with those? We can use our algebra and factor it out. So that's c times a1 plus a2 plus a3 plus dot 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 plus a sub n. Well, what is this? Looking at what we're trying to figure out, we'll have c times, this is the sum of a1 plus a2, a3 all the way up to a sub n. If we take that and write it in summation notation, that will be I equals 1 to n of a sub I. And that is it. Ta-da! And the proof is done, and that is all.